Right. Hey guys. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? I'm good. Our last class session before Thanksgiving, so I think that's exciting news. So after today, we won't see each other for over 10 days. So yeah, it'll be a long time. And so, I definitely want to finish up the lecture notes on rotational dynamics today. And then, if we have time, we'll start the next set of lecture notes too. Okay. All right. And so first thing I want to say, probably the thing that's on everyone's mind is the midterm exams. So I'm still grading them right now. So I'm about 2/3 done. But I do plan on finishing them tonight. And so you can expect to see your scores on Canvas tonight. Okay. And so unfortunately, because of the break, then I won't be able to give them back until afterwards. But like I said last time, if you want to see, how I marked up your exam, you can send me an email and I can scan it to you and send it over the break. Okay. Thing is, I can't do that just yet because there are a couple people that still need to take the exam, and I can't give it back until they've taken it. And so, if you want to see your exam, you can send me an email, but I can't send them out until after that happens. And so, hopefully, I'm hoping to get that done. Hopefully early next week. That's what I'm hoping to do. Okay. All right. And so. Next homework. So homework 6. So I do plan on giving that homework probably sometime tomorrow, probably tomorrow evening. And so keep an eye out for that as well. And so remember, homework 6 is going to be optional for most of the people in the class. If you do it, you'll get about 40 points extra credit for the homework category in your grade book. But if you are a graduate student or if you're taking this class for graduate credit, then that assignment is going to be mandatory. Okay. Okay. I think that's all my announcements. So are there any other questions I can answer before we get started? Okay, all right, so let's go ahead and pick up where we left off. Okay. All right, so where we left off on Monday was we were talking about this idea of inverse dynamics analysis, okay, which is a very fancy, very cool name for something that's kind of more complicated than anything we've done. Right? And so the whole idea with inverse dynamics analysis is that we want to quantify and we want to analyze human motion. Okay. Okay. And to that end, usually what's going to happen is that you're going to be given all of the kinematic quantities. And by kinematic quantities, I mean things like angles, things like angular velocities, angular accelerations. Okay. Okay. So usually those things will be given to you, except in kind of more unique situations. But normally you can count on those. Okay. And again, remember the reason these are usually given to you in these problems is that these are usually easily observed in practice, right? And so you can watch someone throw a baseball, you can watch someone do a dumbbell curl, and then you can observe just how quickly they're doing their motion. Okay. But what you can't really, compute just by looking at someone is, what are all the muscle forces and what are all the joint reaction forces that are happening underneath. Okay. Okay. Because usually from a biomechanical standpoint, that's what we're interested in computing, right? Because that's going to tell us, how hard is this muscle working? How much risk is this person going to be towards injury if they do this motion? Okay? And it's the computations that you guys are going to be doing for your projects as well. Okay. All right. And so I think we left off specifically on a particular example. Okay. And so the example that we were working with is, a gymnast that's kind of doing a Superman pose and being horizontal, holding onto a bar. Okay. And so schematically, it looks something like this. So we have our horizontal bar here. Okay. And so those are the person's hands. Okay. and he's swinging from the bar just like that. Okay? And he's at the perfect moment when his body is perfectly horizontal. Okay. All right. And so what we said was that because the whole body is pretty straight here, we're going to approximate this as a rigid rod. Okay. Where the only force that we have acting on this is the mass. Okay. And so we have the mass times the acceleration due to gravity, and that's happening or occurring at the midpoint of the gymnast. Okay. All right. And if we say that we're interested in solving for the reaction forces here at the bar, okay. And so the way I'm drawing this, it's basically the reaction forces at the bar itself. But you can also think of this as the reaction forces acting at the gymnast's wrists as well, right? Because the wrists are basically going to be sustaining all of this force. And then from here, what we did was we formed the equations of motion. And this was the sum of the forces in the radial direction. Okay. Some of the forces in the tangential direction. Okay. We also had some of the moments around the joint. Okay. Right, so just like we did in the static situation, we're going to have three equations of motion, or three equations that govern the behavior. It's just that now, instead of setting them equal to 0, we set them equal to the appropriate motion terms. Okay. And in particular, just because it leads into the next example, I want to focus just on some of the moments around J. Okay. All right. So we can compute this exactly the same way as we've done before, right? And so we take each of the forces. And so in this case, we have just a single force. And so the force here is going to be mass times gravity. Okay. And then we're going to multiply it by the moment arm, where if we say that the entire length of this person is given as L, okay, then the moment arm between the weight and the joint is just L over 2. Okay. And this is going to be set equal to the moment of inertia of the rod with respect to the joint J, multiplied by the angular acceleration. Okay. And then from this equation, we can compute alpha here. Okay, so we can compute the angular acceleration, assuming that we know what the moment of inertia of this body is with respect to J. Okay, and so we'll do that on we'll complete that on the next page, and then we'll take that piece of information and feed that into the next example, the one that we kind of left off on Monday. Okay. All right. Any questions on this? Okay. And so let's compute, or let's remind ourselves how we compute this I sub j. Okay. And so the way that we can compute this is through the parallel axis theory. Okay. Because we're computing the moment of inertia of this bar, of this rod, at a location that's not its center of mass, right? And so whenever we do that, we have to have two contributions. And so we have one contribution from the, one contribution from the center of mass. Okay. And so we have ICOM. Okay. And then to this, we're going to add the mass of the object multiplied by the distance between the center of mass and the hinge. Okay. Right, and so for this rod, since the center of mass, we assume it to be in the middle of the person, then the distance between the center of mass and basically the hinge is L over 2. Okay. And then for ICOM, we can look this up in a table. And so this is simply 112 ml squared. Okay. And so if we plug all those in, what we get is IJ is equal to 1/3 ml squared. All right, and so if we plug that into the previous equation, we can then solve for alpha. And so if we solve for alpha, what we get is minus mg times L over 2 is equal to 1/3 ml squared times alpha. Okay. And so let's go ahead and start to cancel out some terms here. Okay. And so we see that we have m on both sides, and so those ones are going to cancel. We have an L on both sides, and so that's going to cancel there. Okay. And what we're left with is alpha is equal to minus 3 over 2 G over L. Okay. And so what this alpha tells us is that if the body was rotating as one single rod, under the effect of gravity, this is the angular acceleration that we would have. Okay. All right, and so we're going to use this. Result in the next example, where we consider the body to be two different segments. Okay. All right. Any questions on this so far? Okay. All right. So let's go ahead and go to the next example. And so in the next example, we have the exact same situation. And so we have a person that's that's swinging from a bar. But instead, we're going to consider the body to be made up of two different segments. Okay. And so schematically, it looks something like this. So let's say that we have the bar here. That's the big dot. Okay. And then the little dot is going to be the hinge between the two segments. Okay. And so up here, let's say that we have this is the torso. Okay. And so that consists of the person's arms and their upper torso. And down here we have the legs. Okay. All right, so let me go ahead and label these points. Okay. And so the hinge, we'll call that point O, or the bar, excuse me. And so the hinge in between the torso and the legs, we'll call that point A. Okay, so the point A would basically be your hips. Okay. And then point B would be where your toes are. Okay. Let's assume that the weight is split evenly between these two segments. Okay. And so here we're going to have mg divided by 2, mg divided by 2. Okay. And then let's also assume that each segment has the same length as well. And so let's assume that we have L over 2 and then L over 2. Okay. And so both segments are identical in terms of its geometric and mass properties. Okay. All right. And so, even though these two rods are identical, if you don't do anything, and so if you just let them drop on their own, they're gonna rotate at different speeds. Okay. Actually, it should be alpha 1, omega 1, and alpha 2, omega 2. Okay. Okay. All right. But we don't want that, right? And so if you remember from the example last time, we say that, this person, whether it be, for gymnastics reasons or, for other reasons, this person wants to have it so that both segments are going to rotate at the same time, at the same rate. Okay. And to do that, he has to exert a moment at his hip. Okay. And so in addition to what we have here, there's going to be an internal moment, okay, that's going to be supplied at A. Okay. Okay. So we'll call that MA. Okay. Right. In order to keep this all in one piece. Okay. And so what we're interested in is solving for, what is that moment? What is that MA that the person has to exert in order for them to rotate all as one? Okay. Okay. And then depending on the sign of that moment, that'll tell us which muscles are going to be active. Okay. Because at your core, so at your hip, you have two main muscles. And so you have your abdominals, and so that causes you to do some hip flexion. But you also have your back muscles, right? And so we talk about back muscles a lot in the spinal section. Okay? And so the back muscles will cause your spine to extend. Okay. All right. And so, we're going to go about and solve this problem, given these parameters. All right. Any questions on this? Okay. All right. So let's go ahead and get rolling. Okay. And so since we have two objects here, we have two body segments. We have to do two free body diagrams, and so two sets of motion equations. Okay. Okay. All right, so let's do the torso first. Okay, so remember the torso we're assuming is connected to the bar. Okay. And so here is our torso. Okay. Okay. And so just like we had in the first example, we're going to have two reaction forces at the bar. Okay. And so we have a reaction force OR, and so that's a reaction force in the radial direction. And we have a reaction force O theta, and that's going to be the reaction force in the tangential direction. Okay. All right. You also have the weight. Okay, so it's mg divided by 2. Okay. Right, but we're not done yet. Okay. And so remember, since we broke up the body into two different segments, we're also going to have reaction forces at that joint. Okay. And so, one way that we can describe this is we can say that we're going to have a reaction force in the tangential direction, A theta. Okay. We have one in the R direction, AR. Okay. And we have a moment, MA. Okay. And so these are the reaction forces at the hip. Okay. So this is really important. And so when you're doing inverse dynamics analysis and you're doing it for a multi-segment system, you have to make sure that you supply the reaction forces at the joints wherever you're breaking them up. Okay. And so since we're breaking up this body into segments at the above and below the hip, we're gonna have to draw in the reaction forces at the hip. Okay. And this MA that we have here, this is explicitly what we're solving for. So all this is good. Okay. All right. And so let's go ahead and write out the equations of motion. Okay, so let's first sum up the forces in the radial direction. Okay, so we have some of the forces R. Okay. And so we only have two forces here. And so we have the reaction force at the bar. And so that's O sub R minus A sub R. Okay. Oh, sorry, it's not equal to 0. Okay. So normally this is, because this is in the radial direction, we set this equal to the mass times the centripetal acceleration, right? And so the mass of this segment is m/2. Okay. And the centripetal acceleration, remember, is omega squared times the length or the distance between the joint and the mass center. Okay. And so that's omega squared times L/4, because the total length of this segment here is L/2. Okay. And so this term right here, this is the centripetal acceleration. Okay. All right. But in the end, for this particular problem here, and this isn't true for all problems. Remember, we assume that this person is starting from rest. Okay. And so this whole thing is going to be 0 because we're going to assume that omega is equal to 0. Okay. And so in the end, from this equation, what we have is OR minus AR is equal to 0. Okay. And so, that's our first equation. We can't solve it yet because, both OR and AR are unknowns. Okay. So we don't know either of those reaction forces, but, this is an equation that we can use and, then we'll use it for later. Okay. All right. Any questions on this? Okay. All right. And so that's the sum of the forces in the radial direction. Now let's do the sum of the forces in the tangential direction. So we have some of the forces in the theta direction, okay? And so just like before, we have O theta minus A theta, okay? We also have the weight, and so this is going to, we're also going to subtract a minus mg, okay? And so those are all the forces from our free body diagram, okay? And then we're going to set this equal to mass times A theta, right? Where A theta, remember, this is the tangential acceleration. Okay. Where remember, the way that we compute tangential acceleration is that we can take, the length. Okay. the length or the distance between the hinge and the center of mass, okay? Or I should say the location of the center of mass times the angular acceleration, okay? All right, and so we plug in for this. The mass of this segment is just m over 2, okay? LCOM here is going to be L divided by 4, okay? Because remember, the length of the entire rod is L over 2, and then since the mass center is halfway down that rod, then we do L over 4, okay? And the angular acceleration, remember we solved for this at the beginning of class, right? Okay. All right, and so if you remember from earlier, this angular acceleration was minus 3 over 2 g divided by L. Okay. And so if we perform all this arithmetic here, then what we get is these L's are going to cancel out. And so we have a 3 up top, and we have 2 times 4 times 2 on the bottom, which is 16. Okay. And so overall, this is going to be minus 3 divided by 16 times mg. Okay. And on the left-hand side, we have O theta minus A theta minus mg. Okay. And so that's our second equation of motion. Okay. Which again, we can't solve yet because we have too many unknowns. Okay, so we have O theta and A theta now. And so we have 4 unknowns so far and only 2 equations. And so let's do one more equation for the moments. And I'm going to do something a little bit different this time. And so, what I'm going to do different is I'm going to sum the moments around A, which is going to be our hip joint. Okay. Normally, when we sum our moments, we sum them around the absolute hinge. Okay. And so, or I should say the stationary hinge, okay? And so in this case, that would be the hinge at the bar, right? And so normally what we would do is we'd sum the moments around point O, right? Because that hinge is stationary, okay? But I want to do that, instead I want to do this summation around A, mostly just so that I can show you how to adjust for that, okay? Because what's unique about A is that, as this gymnast goes through its motion, the location of the point A is going to change, right? Because the person is just kind of naturally rotating. And so when that happens, you have to make the adjustment in terms of its moment of inertia. Okay. And so we'll go through that. We'll go through that in a little bit. Okay. All right, but if we sum the moments around A, we can see that we're going to have 3 contributions to the moment. Okay. And so we're going to have one contribution from the weight, first of all, right? And so that's going to cause a moment around the joint A. We have another contribution from O theta, okay? But since we're doing the moment around here, we have a moment arm here of L over 2, okay? And of course, our last contribution to the moment is the actual moment that we're solving for, which is MA, okay? All right, and so if we sum the moments around A, what we get is MA. Okay, so that's the internal moment from the muscle forces. Okay. Then we're going to add the contribution from the weight. Okay. And so for the weight, we have mg divided by 2, which is the weight of the person's body, and then we're going to multiply it by the moment arm, which is L divided by 4. Okay. And then from this, we're going to subtract the moment contribution from the bar. Okay, so this can be minus O theta times L divided by 2. Right. And all of this is going to be equal to IA times alpha. Okay. Where once again, we can plug in for alpha. Right. And so alpha here is going to be a minus 3 over 2 g divided by L. Okay. And so this here is going to give us equation number 3. All right. And so, just by applying the equations of motion to the upper torso of the person's body, we're able to get these equations here. Okay? But unfortunately, we're kind of in a tough spot because we have 5 unknowns overall. And our 5 unknowns are all the joint reaction forces. Okay, and so we have O theta, OR, which are the reaction forces at the bar, and then we also have our reaction forces at the hip joint as well. Okay, and so this is going to be A theta and AR. Okay, and then the last unknown that we have is the moment MA. And so we have 5 unknowns. But so far, we only have 3 equations. And so we can't solve for them yet. Okay? And so we need some more equations before we can actually solve for this. Okay? And those extra equations are going to come from the free body diagram of the legs. All right, and so when you're doing these kind of multi-segment problems, just remember that for each body segment that you encounter, you can write out the equations of motion, and that'll give you basically 3 equations per body segment. Okay. And so for this case, I call it a simple example, but it still takes quite a bit of computation. And so for a 2-segment system, that means we're going to have 6 equations of motion, right? And so we have radial, tangential moment for one, radial tangential moment for the other. Okay. And so what we're going to do next is we're going to write out the equations of motions for the second rod, and then use those to solve for all our others. Right. Any questions on this? Okay. All right, so let's do the free body diagram of the other body segment, okay, which is the legs. Okay, and so here is our free body diagram. Okay, let me go ahead and label these points. Okay, and so since we're on the lower half now, we have our hip joint on the left, and then we have our toes on the right. Okay. So first thing I want to do is, or I guess first thing, let's put the weight. That's easiest. Okay. Okay, so we have mg divided by 2, and so that's acting at the middle of the segment, just like before. Okay. And then we also are going to need to put in the joint reaction forces at A, but you have to be really careful about this. Okay. So let me go ahead and write it down first, and then I'll tell you, how you have to do these. You have to be kind of careful about it. All right, and so you can see here we have AR and A theta, okay? And so if you compare AR and A theta here, you compare their directions, you compare them to our other equation here, okay? Where on our first segment, on the torso, we can see that AR is pointing to the left and A theta is pointing downwards, okay? But on the legs, you can see that we're pointing them in the opposite directions, okay? And this is really important because these reaction forces have to cancel out between the 2 body segments. Okay? Okay, because these are the exact same reaction forces. And so, I'm using the same symbols for these, because they are the same thing, right? And so when you put the two body segments together, these reaction forces have to cancel out. Otherwise, it's just not going to work. Okay. All right. And so the other thing we have to put in here is the moment. Okay. And for the moment's case, in this case, we put that in the should be in the opposite direction actually, because we have basically the same thing. Okay. So it should be this direction. Sorry about that. That's what I was checking. That's what I was checking in my notes, because it's should be in the opposite direction. Okay. And so in the other in the other case, we have it in the counterclockwise direction. Here we have to do it in the clockwise direction for them to cancel out. Okay. All right. And so just like we did before, we're going to write out our equations of motion. Okay. So first, let's write out the some of the forces in the radial direction. Okay. Oh, and notice that we don't have any reaction forces at B, because B, our feet are just kind of dangling in the air. Okay, and so because B is not contacting anything, we don't have any reaction forces there. Okay. All right, and so if we sum up the forces in the radial direction, we see that the only one that we have is AR. Okay. And just like before, this is going to be equal to the mass, okay, or minus the mass, multiplied by the centripetal acceleration of the segment. Okay, so we have omega squared times the distance, the distance between this mass center and the absolute or the fixed hinge. Okay, and so for this one, it's going to be 3L divided by 4. Okay, because everything is rotating around a hinge, which is kind of on this side of this side over there. Okay, but once again, we're assuming that we're starting from rest. Okay. Right. And so in the end, what we get is, because omega is equal to 0, we have AR is equal to 0. Okay. And if AR is equal to 0, if we look back at our equation of motion from the last one, okay, we have OR minus AR is equal to 0. Okay. And so if AR is equal to 0, this means that OR has to equal 0 as well. Okay. And so we've solved for two of our unknowns kind of straight away just from this. Okay. All right. And so with that, with those two out of the way, then we can just focus on our last three unknowns, which is A theta, O theta, and MA. Okay. All right. Any questions on this? Okay. All right. And so let's go ahead and write out the other equations of motion and then solve it from there. Okay. All right. And so let's go ahead and sum the forces in the theta direction. Okay. And so if we sum the forces in the tangential direction, what we get is A theta minus mg divided by 2 is equal to mass times the tangential acceleration of this of the mass center. Okay. Okay. Where just like we did on the first segment, the tangential acceleration is going to be the product of the location of the center of mass, okay, multiplied by the angular acceleration. Okay. And so, LCOM here, this is going to be 3/4 L. Okay. Because the location of this mass center is 3/4 times L away from the pivot. Okay, the fixed pivot. And then just like before, our angular acceleration here is a minus 3/2 times g divided by L. Okay. And so we plug all this in, and then we move this mg/2 over to the right-hand side. And what we get is A theta. A theta is equal to minus 5/8 times mg. All right. And so that's one more unknown down the hatch. Okay. And so we can't solve for O theta yet because O theta, the equation for that was a little bit more complicated. Well, actually, we can. We actually can solve for O theta in this one, but it's actually not that important. Okay. And so what's going to be important is the moment equation, which we can use to compute the MA. Okay. All right. And so just like we did before, let's sum the moments around point A. Okay. And so if we sum the moments around point A, what we get is we get a minus MA, right? Because the MA is a clockwise moment, and so we have to do a negative there. We also have a contribution from the weight. Okay, so we have mg divided by 2 multiplied by L/4. Okay. And this is equal to IA times the angular acceleration alpha. And so we have the angular acceleration, okay, and so that's fine. Okay, so we know this is going to be equal to a minus 3/2 g/L. Okay. But what we don't have here is IA. Okay. And this is complicated because the location A, or the hip joint here, is actually going to be physically moving, and so it's not a fixed pivot. Okay. All right. And so whenever you have a rotation point which is not fixed in space, then you have to adjust for this. You have to adjust for the moment of inertia to account for the fact that this point is going to be moving. Okay. And so that's what we're going to do on the next page. All right. Any questions with this? Anything we've done so far? I know it's a long example, but that's kind of how it is here for inverse dynamics, is that there's kind of a lot of calculations that we have to do. A lot of steps, but a lot of the steps are thankfully the same. It's just that you kind of have to be a little bit organized with your algebra, just because there's kind of a lot of terms going on. Okay, and so let's go ahead and write out that moment of inertia. Okay. Or in particular, let's write out that entire term. Okay. And so that entire term, we have I times A multiplied by alpha. Okay. We can split this into two different contributions. Okay. Right, and so we're going to have one contribution that has to do with the center of mass. Okay. Okay, so I'll call this the center of mass contribution. Then we have another contribution, which is what I like to call the movement contribution. Okay. And so if you look at the structure of this term, it's similar, but it's not quite the same as our extra term in the parallel axis theorem, right? And so remember, when we use parallel axis theorem to compute a new moment of inertia, just like that one, we have a center of mass term, but we also have an additional term to account for the fact that it's almost like an adjustment term, right? And so we have to adjust our calculation based on kind of a unique situation, okay? And that's what we're doing here. And so there's three terms in this expression here, okay? And so I'm going to go through each one individually. So probably the most unknown one here. So we have RAE, okay? Okay, and so this RAE is going to be the distance between the rotation axis and the center of mass, okay? Which, I know I've used the term rotation axis to refer to a couple of different things, okay? And so this rotation axis refers to this point right here, okay? And so, for our example here, where we have a rod that's like this, okay? And we're summing the moments around this point A, okay? This RAE is going to be this distance right here. Oops. Okay. Because this location right here, this is our center of mass, right? And so RAE is the distance between, whatever point that we're summing around, okay? And so in this case, it's point A and our center of mass down there, okay? Number two is m/2. Okay, so this one's pretty straightforward. So this is simply just the mass of our rotating body. Okay. And then three here, this is the tangential acceleration of the point A. Oh, not a point A, I'm sorry. So this is the tangential acceleration of the center of mass. And so, we're just going to use the same tangential acceleration that we did from the previous equation and then plug that into here. Okay.
This is for the movement, right?
Exactly. Yeah. So all these purple terms have to do with these guys up here. So I basically said that this is term 1, this is term 2, and this is term 3. So I'm just kind of explaining where each of them come from and how you compute them. Okay. All right. So it's a lot to plug in, and so we're going to go ahead and do this slowly. Okay. All right. Any questions on this? Okay. All right. And so let's go ahead and plug this in. Okay. Plug this into this equation here. Okay. And then we're going to perform all the arithmetic and ultimately solve for MA. All right, and so we plug all these in, we get, on the left-hand side, we have minus MA minus MGL over 8, okay? And so that MGL over 8 came from the moment term of the center of mass, okay? And then now we're going to plug in everything from the previous page, okay? So first thing we have is we have the center of mass term, and so we have I of the center of mass, which is 1/12 times the length squared. Okay. Okay, so that's L squared over 4. And we multiply by m/2 because that's the mass of the rod. Okay. And then we're multiplying this by the angular acceleration. So this is minus 3/2 g over L. Okay. And then to this, we're going to add our motion term, right? And so our motion term is L over 4. Remember, this is RA sub slash E. Okay. Multiplied by M over 2. Okay. And then we multiply by the tangential acceleration, which we computed from before, is minus 9 over 8 times G. Okay. All right. And so if we solve for MA, we have MA is equal to, and if we plug everything in here and perform all the arithmetic, we have a minus mg L divided by 64 minus, and then we perform the arithmetic for this term, so minus 9 mg L divided by 64. Okay. Oh, sorry, there should be a minus sign out here. Okay. Plus, and so we're going to move this mgl over 8 to the other side. Okay. And so we add up everything. Okay. We add up everything and we get MA is equal to, finally, minus MGL over 32. Okay. And so based on the sign of this moment here, we can see that the sign is negative. And so if the sign is negative, that means MA is going to be rotating in the clockwise direction. Okay. Where did the minus 9 over 8g come from? Yeah, that's so this was a theta. So that was our tangential velocity. Yeah. Yeah, and so we computed that a theta from the previous equation when we summed up the forces in the theta direction. Yeah, so it was basically the product of these two terms. Okay. And so since the moment that we ended up with at the end was negative, that means that the body kind of has to there has to be kind of a clockwise moment to kind of bring the two segments closer together, right? And so that tells us is that if you're swinging down like this, in order to keep your body completely straight, then you have to flex your abdominals a little bit just to kind of bring your legs closer to you. Okay. Because what's going to happen is that your legs, because they're farther away, they're going to want to do this kind of naturally. And so you need to flex your abdominals to kind of bring things closer together. Okay. All right. And so that was a really long example. And so that took us, almost an hour to do. So, I know it's a lot of calculations for these, but, that's kind of what inverse dynamics is all about. All right. Any final questions on this example here before we move on?
So the muscle force of the abdominals is counteracting clockwise moment.
Exactly. Or it's generating that clockwise movement. Yeah. And so if you actually wanted to solve for that force, and so I know it's kind of weird to express this in terms of a moment, right? But you can just do a simple free body diagram. And so if you make a free body diagram, and so this is say that we want to compute the muscle force. Right, because we haven't computed a force yet. We've computed just a moment. Okay. And so we want to compute the muscle force. You can just draw a free body diagram here. Okay. And let's say that the person's head is over here, and the hip is over here. Okay. Right, and he's facing down this way, and so the abdominals are going to basically perform, an action like this, right? And so we're gonna have FM just like usual, okay? And so FM is gonna be, acting with some muscle angle theta m, okay? And so what we just computed was that, the amount of moment that the abdominals have to create around the hip joint is is minus MGL over 32, right? Or the magnitude. Let's just take the magnitude of this. Okay. And so the magnitude of this moment is MGL over 32. Okay. And so what you can do is you can just sum the moments around this joint. Okay. Set it equal to MGL over 32. Okay. And so this is going to be equal to, and say that, we have this attachment angle LM, okay? And so this is going to be equal to FM LM times sine of theta m, So pretty standard as we always have done, okay? And so this tells you that FM is equal to 1 divided by LM sine theta m times MGL over 32. You can ignore, because normally, we have the weight of the objects here and everything like that. But for something like this, you can just kind of ignore those things because we have already taken into account all the weights of the different segments and all the reaction forces. We did that in our inverse dynamics analysis. Okay, and so here we're basically just transforming or translating the moment that we computed to a muscle force. And so the only thing you have to do is just divide by the moment arm of that muscle. Okay. All right. Any questions on this?
Like if you were to swing from a bar, flex your from horizontal and not flex your abs, like wouldn't the legs want to naturally go clockwise? Like we're thinking from this position, wouldn't they naturally want to go clockwise? So like, why don't your abs produce a counterclockwise?
Yeah. So the it's a good question, and so I think it's because the torso is closer to the bar, and so it's naturally going to want to rotate a little bit faster than the legs, and so you basically have two segments right here, right? Right. And so your two segments are going to rotate at different speeds. Okay. But because this segment here is closer to the point of rotation, there's less resistance for it to rotate, right? Because the moment of inertia of just this segment is just it's a lot closer, and so it's going to be a lot easier for it to rotate. And so this one's going to want to rotate faster than the legs over here. And so if you don't do anything, you're going to end up in a situation like this, where this one has rotated maybe by this much, your legs have only maybe rotated by that much. Exactly. Yeah.
Okay, I was imagining your legs going first.
Oh no. Yeah. So the legs are going to rotate. They're going to lag behind because there's a higher moment of inertia for the legs. Yeah. Mm-hmm. All right. And so for the last 15 minutes today, I want to talk about how you can perform inverse dynamics analysis just in general. Okay, so we did it for a 2-segment system, but you can generalize this to act on like a 3-segment system, a 4-segment system, and so on and so forth. Okay, it's painful, and so it's it takes a lot of computations, but that's kind of how a lot of this biomechanics analysis is done on moving objects. And so even though the amount of computations that you are going to have to do are growing, the same process is going to be applied, and you're going to be given the same information. Okay, and so just like we saw in the previous problem, you're going to be given you're going to be given all the kinematic variables. Okay. Right. And then from those, you want to compute, what are the internal reaction forces and internal moments needed to generate this motion. Okay. And just like I mentioned before, that this is not just limited to biomechanics, although it's certainly useful here, certainly. But it's used a lot in robotics too. And so anytime you have any kind of mechanism that has multiple segments that all have to kind of move together, then inverse dynamics is a great way to perform that analysis. Okay. Okay. And so let me do another example. I'm not gonna put any numbers on this because I think that's the challenging part. But I will show you how I would set this up. Okay. Because I think once you kind of understand kind of the general process of the setup, then then all the details, all the computations are just a lot of algebra. Right? Not saying that algebra is easier or not, but it's more systematic. All right. And so let's do an inverse dynamics analysis of a leg. Okay. And we'll consider 3 segments. And so we'll consider the thigh, we'll consider the shin or the lower leg, and we'll consider the foot. Okay. Okay. And so kind of a very simplified way that you can say this is say that, we'll say this is the thigh. Okay. This right here is the lower leg or the shin. And this right here will be the foot. Okay. Right. And in terms of the joints, we have 3 joints here that we can consider, right? And so we have the ankle joint, and so we'll call that A. We have the knee joint, which we'll call K. And then up here, we have the hip joint, H. Okay. All right. And so, what we can get from inverse dynamics is we can compute all of the muscular moments and all of the reaction forces at each of the joints. Okay. And so you can do all of them in this case. Okay. All right. And the way you set this up is, we're basically going to follow the same process that we followed in the previous example. Okay. And so we're going to go segment by segment and draw out the free body diagram on each segment. Okay. And so I'm going to go from the bottom up. So we're going to go from the foot, and then we're going to go up from there. Okay. And we'll assume that the foot is on the ground. Okay. And so there's going to be a normal reaction force on the ground right here. Okay. So that's going to be the only external force that we're going to consider. All right. Any questions on this so far? All right. So let's go ahead and write out all of those free body diagrams. Okay. So let's start with the foot. Okay, so the foot looks something like this. Okay. Okay. And so the foot has its own mass, and so we'll call that the mass of the foot times gravity. Okay. We have the normal force from the ground. Okay, so that's the external force. And then we also have the reaction forces at the ankle. Right? So AX, AY, and we also have a moment. Okay. It doesn't really matter, what direction you put the what directions you put the reactions on a particular segment. You just have to make sure that you do the opposite directions on the other segment. Okay. So that's the foot. Now let's do the shin. And so the shin was something like this. Okay. And so we have the weight of the shin. Okay, so this is going to be M shin times gravity. Okay. We have the reaction forces from the ankle, right? And so we have to choose the opposite directions for these. Okay. And so on the foot, we see that we put AX pointing to the right. And so here we have to put AX pointing to the left. Okay. Same thing for AY. And so we're going to choose the opposite direction for AY. Okay. And then for the moment, we're going to put it in the opposite direction. Okay. And so if we did clockwise for the moment there, we're going to choose counterclockwise for the moment here. Okay. Right. And then now we have the reactions at the knee. Okay, so we have KX and KY. And then we have MK. Where again, you're going to be given, I forgot to write this. And so for the foot, we're going to have omega foot and alpha foot. And for the shin, we're going to have omega shin and alpha shin. Okay, so remember, those are going to be given to you. Okay, and you're going to be interested in solving for all of these internal quantities. Okay. All right, and we have one more, which is just the hip. Okay, I mean the thigh. And so once we write that, then we'll wrap it up for today. Okay. All right. Any questions on this? Okay. All right. So let's do just one more with the thigh, and then we'll be done for today. All right. So for the thigh, we're going to have omega thigh and alpha thigh. Okay. Okay. And so just like before, we're going to have our weight. Okay. And so this is the mass of the thigh times gravity. Okay. We have our knee. Okay. Remember, we're going to put these in the opposite directions. Okay. And then we have the reactions at the hip. Okay. And so for the hip, we have HX, HY, and then MH. All right. And so if we count up all the unknowns and we count up all the equations that we get, we will see that we have 9 equations for our 9 unknowns. Okay. Okay. Because for each body segment that we have, we're going to have 3 equations of motion. And so since we have 3 segments here, we're going to have 3 times 3, which is 9. Okay. And our unknowns Our unknowns in this case are all the reaction forces at the joints. Okay? And so since we have 3 joints, we're gonna have three unknowns per joint, and so that's gonna be 9 unknowns. Okay? And so we have a perfect system that we can solve for all of the unknowns. It's just gonna be a painful process because 9 equations, 9 unknowns is not a fun thing to do. Okay. One last point I want to make, before we wrap up, and maybe you know this already, just kind of based on your previous classes. But if you notice, for all of these free body diagrams, we have multiple moments, okay? And they're applied at different locations in the segment. Okay? And so I think a fair question to ask, or some people might ask, what happens when you have these multiple moments? And so how do they factor into the equations of motion? Okay. Right. And so the way that you factor them in is you basically assume that because these body segments are assumed to be rigid, we assume that these moments are applied all throughout the entire segment. Okay. And so when you're summing the moments around this, or summing the moments for this body segment, and so let's say that we sum the moments around the hip, okay? And so for this case, we're going to have both of our moments here, and so we have minus mh because mh is going in the clockwise direction, and since mk is going on the counterclockwise, just going to add an mk, okay? And of course, we're going to have other contributions from the weights and the reaction forces and things like that. Okay. But when you sum the moments around a rigid body like this, it doesn't matter where the moment is being applied. You just add them all up because we assume the moments are applied throughout the entire body. Okay. All right. And so when you're doing inverse dynamics analysis, with these kind of multiple moments, that's kind of how you do it. All right. Any final questions before we wrap it up for today? Okay, all right. And so, I had actually planned to end a little bit earlier, but we're basically right at the end. So, I'm sorry about that, but have a great Thanksgiving, everyone. Have a great fall recess. And so, hopefully everyone, I know everyone will be catching up on work over Thanksgiving, but hopefully you're able to rest a little bit and spend some good time with family. So, I'll be available, almost the entire break. And so, Thursday, Thanksgiving, of course, I'll be with my family. But if you have any questions about the project or anything, please don't hesitate. So. I'll see everyone after the break. Have a great break. I'll see you guys after that. Okay. Okay. That's no problem. We're doing the answers activity today. So.
That's why I don't want to be that late.
Okay.
So I'm just going to try and as long as I can.
Okay, sounds good. Yeah.
Take care, Dr.
Thanks, you too. Have a good break. Thanks, guys. See you tomorrow. The project is going to be like a bigger version of the case study? Pretty much. Yeah. Yeah. So the homework, all the homework reports are in preparation for the big project.
We contacted the person, but never replied back.
Oh, really? Okay. Because actually last time he said he contacted you guys, but didn't.
Yeah, he did,
Uh-huh.
but then we set up a Discord and texted him, but.
Okay.
that was it.
Yeah, so I'll talk to him and, you know,
Yeah.
make sure he gets back to you guys.
Okay, we'll see what it says, yeah, because he provided us with a phone number.
Mhm.
I created a group chat between us three.
Uh-huh.
And I sent a link to a Discord that I created.
Yeah. Okay. Okay, let me talk to him and then I'll get you guys all an email together just to make
Okay.
sure, you know, everyone's on the same page. So, yeah, thank you guys for doing that, by the way.
Yeah.
Really appreciate it. Have a good Thanksgiving, guys.
Yeah, you too.